Last time we talked about the Picard-Lindelöf theorem. And so this theorem is about solutions to ODEs. And so specifically, it's asking that, so you have a function f and a function g, and f here is differentiable, and the derivative of f as well as g are continuous. And then the problem is that you're looking for solutions, so you want a solution, so looking for a solution y to the ODE, and the ODE is that the derivative should be equal to f of y. So at some point x, the derivative of y should be equal to f of y of x plus g of x. And you are looking for that, that this function, that y of 0, say, is equal to a. Okay, so this is what's called the initial condition. Right, and this is ODE, and this is equal to that. And so, in order to, so we want existence, so want existence and uniqueness. So existence just means that there is a solution for a given A, there is a solution. Uniqueness means that if you have two solutions to this ODE, then they will have to coincide. Okay. And so the way we were setting it up was that we were using the contracting mapping theorem. So the contracting mapping theorem is the following, that if you take a metric space X, and this metric space is, so X comma D is a metric space, is a Cauchy complete metric space. Then a contracting map, so a contracting map is a map T from this metric space into itself, so that and a constant C strictly less than 1, so that if you measure the distance between the images, the images are squeezed together. So this means that the distance between the images is this constant that is strictly less than 1 times the distance between x and y. So this is a contracting map. And the contracting mapping theorem say the contracting mapping theorem is the following, that there exists if you have a Cauchy-complete metric space and you have a contracting map like this, then T has a unique fixed point. And remember that a fixed point, this is an X in this space, so that T leaves its invariant. Okay? And so we proved this, we proved the contracting mapping theorem last time. Now, how were we going to use this for this ODE? So we defined, so if I here is an interval containing 0, then we defined and u is a function, y is a continuous function. Then we defined t of y. So this is a continuous function on the interval, on I. Then we defined another continuous function on the same interval as follow, that the t of y, so this is going to be a continuous function. So in x, this thing here is, this is a, because we want it to have value at 0, a, and then we're integrating from 0 to x of f of y of s plus g of s ds, right? And so this here gives you a map from T, gives you a map from the continuous function on this interval into the continuous function on the interval. And it also has the property that if you take a function and you evaluate it at 0, then you get A. Okay? And now we observe that, in fact, the image here, the image is, if you define, when you define it like this, by the fundamental theorem of calculus, this function here is differentiable. So this function is, so it actually takes, so T actually takes the space of continuous functions into the space of functions that are not just continuous, but actually differentiable, and even the derivative is continuous. And the ones that are, so this here is a space of functions, so this is functions that are where the functions y, so that y prime exists and is continuous. Okay. So, right, and so now what we saw last time was that by the fundamental theorem of calculus, the derivative, right, so by the fundamental theorem of calculus, the derivative of this function, if you take y and you take t of it, This is now a function, and it's differentiable, and the derivative is f of y. So at x, it's f of y of x plus g of x. And so this means that if y is a fixed point for the map T, so if it's a fixed point, this just means that T of y is equal to y. Well, then, then this thing here is the derivative of y. So then it means that y here solves the ODE. Right, we have already checked that the initial value, we did that somewhere here. We already checked that the initial value is what it should be. And if it's a fixed point, then the derivative is also what it should be. Right? Okay, so we want to find a fixed point. And so what we did last time was that we saw that if we restrict the interval, so last time, what we proved is that if we restrict the interval, so last time we showed, so we set m here equal to a, absolute value of a, plus 2. And then we saw that there exists a delta 0, at delta 0 greater than 0, such that if you restrict to the interval, if you're looking at the interval of continuous function, so the interval of continuous function on this little interval, so this is an interval around 0, and you're looking at this map, then this map here, well, first of all, we already know that it takes the space of continuous function into the space of continuous function. But we have something more, that we have that if you're looking at the subspace of this, which is the space of functions y that are here, and you also require that the norm here is less or equal to m, then T takes this space here into itself, right? This is this lemma that we proved last time, right? And so, okay. So, so this space here, right? You can think about this space here as we did last time, as so then we define capital R equal to, no, actually, sorry, we defined, we looked at the balls, I guess, just on this. So we looked at the ball of radius capital N in this, around the 0 function. So this thing here is the closed ball in the space of continuous function with the metric that we've been using. And this set here, we can think about if we want as this set, okay? Okay, so now what we have is, so the setup now is that we want to find a fixed point for this map T, right? We have a space that we want to look at, and the space is, again, now we're going to think about, so this is the space we're looking at, but this is what we before have denoted. Like the ball in this metric space, it's centered at the function that is constant 0, and this is the radius, right? And so I'm now looking at this map. So we have now shown that it takes this metric ball into itself, okay? And I want to find a fixed point. fixed point of t. Okay, so I need to show, so we want to show that T is a contracting map. Right? Because if it is a contracting map, then we already know that if you take a closed interval like this and you equip it with the usual distance that we have, this here is Cauchy complete. Right? But now if you take a Cauchy complete space and you're taking a closed subset, and this here is a closed subset, then this here is also Cauchy complete. This here is also. Okay, so if we could prove that T from this space into itself is a contracting map, so it means that there exists this C strictly less than 1, then we would have a fixed point and we would have a solution to the ODE, right? The thing is that this is not quite going to do it. It's not quite a contracting map. But so we will need, for it to be a contracting map, we need to restrict the interval further. Okay, so by that I mean that we need delta to be, we need to show that there's some delta. It will actually be less than, so we need to show that there's some delta that is smaller than this delta 0, and so that if you restrict to this space here, now it's a continuous function. I won't I will denote the ball by the same. But this here is actually a ball in a different metric space, because this is now a ball in the continuous functions on this smaller interval. Okay, but it's not for the same radius. Okay, so if we restrict the map to this space here, then on this it is a contracting map. Okay, so we need to cut down the interval. Okay, so now how do we do that? So we need the contracting property again. And so suppose you take two functions. These are continuous maps on some interval, say from right here. Again, delta is now, that's the delta we're looking for, and it would be smaller than delta 0. So since it's smaller than delta 0, we already know that so we have two maps like this. They are both supposed to be in the ball, so this means that this thing here is less than m. And we know, we have already proven, just because delta is less than delta 0, that t of this function here has norm less or equal to m. Okay, so but now let's look at the difference. So t of y1 of x minus t of y2 of x. Right, and we're interested in the norm here. And now x here is in this smaller interval. Okay, so now let's just write down what the map is. So the map here is the integral. So it's a plus the integral from 0 to x of f of y1 s plus g of s ds minus a plus the integral from 0 to x of f of y 2 s plus g of s ds. Right? And now you see that the a's cancel, right? The a's here cancel. And the g of s, those also cancel out. Right? So you are left with that this thing here is the absolute value of the integral from 0 to x of f of y1 of s minus f of y2 of s ds. Now, so last time, when we proved that the map T takes this ball into this ball, we defined, so let me just define that again. We defined L1, and N1 was the maximum of actually I don't remember whether it was called L1. Let me just call it L to not call it. So L here is the maximum of f prime of Z, where Z here has norm less or equal to m. Okay? So this is, so f prime exists and is continuous. So on this interval here, it has a maximum. Okay? So it's a nice finite number. And so now we use so by the mean value theorem, by the mean value theorem, we have that f of Z1 minus f of Z2, as long as Z1 and Z2 are in the interval from minus m to m, then we have that this difference here is equal to the derivative in some intermediate point, sigma, psi, I guess, psi, times the difference between the two, Z1 minus Z2. So we have this, right? This is the mean value theorem. And so we have that, therefore we have that the norm here of the difference is bounded by this here. When we take the absolute value of this, we're getting the absolute value. So this here is equal to the absolute value of f prime sigma times Z1 minus Z2. This thing here, because these two are in this interval, this is bounded by capital L. So you're getting this. And so now, if you use this fact here, and you use this on this, so this thing here is less or equal to the integral from 0 to x, and I can take the absolute value in under the integration sign. So I get f of y1 s minus f of y2 s ds, right? And so now I can continue this string So I have, what I'm interested in is t of y1 at x minus t of y2 of x. And I'm interested in the bound for the absolute value. And I have that this is less or equal to the integral from 0 to x of f of y1 s plus f of y2 s ds. And now I know that this interval here, right, x is supposed to lie in this interval here. So this means that the length of this interval from 0 to is at most delta. So delta. And then I can take the maximum of this, or I can take the, that's right, I can take the maximum of this, but you see that this thing here is bounded by, so this is the maximum, and if I use this inequality here, it's bounded by L, and then it's applied, this here you should think about as Z1, and this here for each x, you can think about this as Z1 and Z2, and so you're getting this thing here times y1 s minus y2 s, and here s will now lie in the interval, in this interval here. Oops. Right? And so now you see that this is just a constant. So this is equal to delta L, and then this maximum S less or equal to delta y1 minus y2. Like this, right? This is evaluated in S, but I don't write that. Okay, and this thing here, but this is just delta L, this maximum here is just the distance between this function and that function. That's how we define this distance, right? And so you see that this right-hand side is now holds for all x. So this means that we have that the maximum of this thing here over x, where x is in the interval between 0 and delta. So this means that we have that the distance between t of y1 and t of y2, this thing here is equal to the maximum. This is how we define that distance after all. And then it's of this thing here. X minus t of y2 in x. Right, so we have that this and this inequality say that it's less or equal to delta L d y1 comma y2. And so you see that now so L here was just a fixed constant, right? If I now set delta, just to make sure that there's no problem, I'm setting delta equal to 1 over 2L. I don't really need the 1, but I'll just do it like this so I don't have 0 in the denominator. If I choose the delta to be equal to this, right? Well, then you see that this thing here, the inner product of these two is less, or the product of these two is less than a half. So this is less or equal to, I can just place it by a half. Like that, right? And so you see, this is exactly what it means to be a contracting mapping. In fact, it's a contracting mapping which is pretty nice, that the constant, it's not just strictly some constant strictly less than 1, but it's actually a half, right? So it's a contracting mapping theorem, a contracting map. And so now by the contracting mapping theorem, we have a fixed point, okay? So this solved the ODE, okay? And it does more than that, because the contracting mapping theorem said that it has a unique fixed point, right? So this means that, and if you have a solution to this, right? If you have a solution to this, then we saw last time that if it is a solution, then it is a fixed point, right? Okay, so now we almost have existence and uniqueness. Let me explain what is missing to the existence of uniqueness. So for that, let me backtrack a little bit and talk about something about metric spaces. Specifically about connected metric spaces. Okay, so suppose you have a metric space. Then we say that it is connected if X here is the only subset, so the whole set itself is the only subset of X that is both open and closed. Right, remember that if you take a metric space, then if X and the empty set are the only subset of X that are both open and closed. Right? Remember that if you take a metric space, and if you take the whole set or the empty set, they're both always closed and open, right? And so it's connected if those are the only two subsets that are at the same time open and closed, okay? And so now we have the following lemma or theorem, let's call it theorem, that if you take an interval here with a usual metric here, so I here is an interval, then the theorem is that this metric space here is connected. Okay, so let's try to prove that. So I take now a subset here that is both open and closed. And we want to show that if A here is non-empty, then it implies that A is everything, right? So we're assuming that it's non-empty, and then we should try to prove that A is everything. So we let X0 be an element in A, right? We're assuming it's non-empty, so we can let X0 be an element in A. And now I want to define, so I have here my interval. This is my interval I have here X0, and I take, and I'm looking at the y in A, so that that if you take everything, so y is in A, and I'm going to look at y in A with y bigger or equal to x0, and I'm going to look at the y so that this whole interval here from x0 to y is contained in A. So I'm defining, so define as subset here B of I, so that it's the y, this subset B is the y in A with the property that that y here is bigger or equal to x0, and you have this interval here is contained in A. Okay? And now I want to show that, so let's say for the sake of argument, let me assume that this interval is a closed interval like this. It works equally well. The argument with obvious modification works equally well if it's open or half open interval. Okay. So I take some y here, and I have a y, and y is, so it's a set so that this whole interval is contained in A. Okay. And what I want to show is, that y is in A, and this is the first thing I want to show. One is that y is in A, and then the second thing I want to show is that y is equal to B. You see, if I had proven both of these properties, right, then it would be that, so then it would mean that everything here would be in A, and including this last point, right? And so this means that we have this entire interval is in I, and then likewise we could argue on the other side, okay? So now, how do we prove this? So, well, the first thing is that if we take, so if we set, sorry, this is, no, sorry about this. This here should have been y0, and this should have been the sup of a y in A. Sup of these guys. And then this here, and we want to prove that this thing here is in A. And the second thing is we want to prove that this sup is actually equal to B. Okay, that's what we want to prove. Right. So the sup of these, well, if y0 is the sup of elements, then you have a sequence. So here you have y0, and this means that you have a sequence of elements which are then in elements in the set B. This is sup of B. Mine. This is the same. Sup of B, sorry. Sup of B. I'll write it like this. So I take this set, and these are the y so that this entire interval is contained in A, right? And then I take the sup of this set, and I want to prove that this sup is in A, and then I want to prove that, in fact, the sup is B, okay? So that it's the sup of such elements in capital B means that there exists a sequence of elements in B, so that y here, y0 is the sup of B. This here implies that there exists a sequence yn, and these yn are in A, and you have that x0 yn is contained in A. And then you have that these guys converge to y0. Right? This is what you get from that is a sup. Right? These two things are that the elements are in that these elements. So this here is just that the yn on B. Right? Okay. So now what you have, so this here means, so here I have x0, here I have y0, and I have these elements, yn, and they are, in particular, they are in A, okay? But A is closed, right? Since A is closed, since yn is in A, and yn and A is closed, is a closed subset. This means that that the limit here, the limit y0, which is the limit, this here must also be in A, right? Okay, so we have proven the first property, right? We've proven that right, so we've proven that y0 is in A, but now you see that we have that for each of the yn, we have that this interval here lie in A, right? And they converge to this. So it means that if you take anything to the left of y0, well, then eventually there's some yn to the right of that. And so this whole interval is in A, right? So you see that this, it now means that not only is in y0 in A, but y0 is really in the set B. Okay? This here only used that A was closed, right? So now we need to use that A is open, right? So now, suppose we take an element. So now here we have x0. We have here B. And we want to show that this y0 we define to be the sup of this set, capital B. We want to prove that this thing here is in fact y0. Right? Suppose not. Suppose not. So suppose that you have here, strictly between these two, this here is y0. Right? Now we already know that y0 is in A. This is what we proved here, right? So, but since A here is open, there exists some tiny little interval. There exists some interval here around this y0. So if you take y0 and you subtract this epsilon, so there exists some epsilon greater than 0, so that if you're looking at this tiny little interval centered at y0, then this here is contained in A. This is just because A was open, right? But this means that now you have that, so this here is, you assume this here is y0, so you have that this thing here lie in the set capital A, and this here guarantee you that you can actually go a little bit past it, right? That even if you go a little bit past it, if you go a little bit past it here, then these are still in A, right? So this means that this could not be the soup, right? So therefore, this point here had to be B, right? It had to be the final point. Okay, so this proved this true property, right? And so once you have these true property, you have that the interval is connected, right? That the only non-empty subset of the interval that is both open and closed is itself. Okay. Now, why is this related to what we want? So this is just, so we have, suppose you take two functions. So why is this related to the uniqueness for the ODE? So this is the following lemma. Suppose you have an interval, so this is an interval in R, and suppose you have two functions, u1 and u2. They are functions on the interval, and they are both continuous. And then assume that for some x0 in the interval, u1 of x0 is equal to u2 of x0. So they coincide in one point. And assume you have a second condition, and the second condition is that if u of u1 of x is equal to u2 of x, then there exists a neighborhood, so a epsilon, where this is allowed to depend on x, so that u1 is equal to u2 in not just at x, but actually on this little interval, x minus epsilon, x plus epsilon. Okay, so you have these two properties. So you have two continuous functions on an interval. They agree at one point. And if they agree at any point in this interval, then they agree on a little neighborhood of that point. Okay, but the neighborhood may depend on the point. Okay, and then the statement is, so the claim is that u1 is actually equal to u2 everywhere. In the interval where they're defined. Okay, that's a claim. Okay, and so now you see that if you take if you're looking at, so the proof of this is that suppose you define a function, and this function here is u1 of x minus u2 of x. If you define it like this, u1 and u2 are continuous, so f here is continuous. You also have that f of x0, well, this is u1 of x0 minus u2 of x0. And these two functions coincided at x0, so this is 0. You also have that if f of x, so if f of x is equal to 0, well, right now, then you have by this second property here, this property here. So if f is 0, this is just meaning that the two functions coincided at that x. So this means that they exist at delta, epsilon greater than 0, such that f of y is equal to 0 in this little interval around x. Right? So you have that. And now I claim that, so now the claim is that the 0 set, so the set where the function f is 0, this is both open and closed. So the claim here is that the set capital A, this is the set of x in the interval where f of x is equal to 0. That this here is both open and closed. Right? We already know that this set, this is followed up here, that x0 is, so since x0 is in this set, then we have, and the interval is connected, and I is connected. If this set is both open and closed, then we have that, then A is equal to the whole interval, right? So this means that that f is constant 0, which means that the two functions coincided everywhere, right? And so we just need to prove that f is both open and closed. But the 0 set, if you take a continuous function, right? So if f here is continuous, and you have a sequence so that each element here in the sequence is 0, and these xn converts to some x, well then by continuity, right, by continuity, f of x would also be 0. This is by continuity, right? We already. So this means that this set here is definitely closed, right? And the open thing, well, the open is just exactly this property that we are assuming, that if you have an element in it, each element is interior, which means that there is this little interval around it, right? So we have proven that it's both closed, we proved that first, and also open. And so we have that if you have two such functions, defined both continuous and defined on an interval, they coincide at one point. And if they coincide at one point, then they coincide in a little neighborhood. If you have two functions with this property, then they must be equal in the whole interval. Right? Okay. So now, how does this relate to the uniqueness that we wanted to prove? So we're starting again. So this is again the Picard-Lindell theorem, and this is the uniqueness part. And so you're looking at, again, solutions to this ODE. And we have that now, we have that and then we let y1 and y2 be solutions. And let's say that these two, they may be defined on different intervals. Of course, but you just take the intersection of the two intervals that they're defined. So suppose that they're both defined, say, on the same interval. Like this. And this interval here, and I, of course, has to include the 0 where we want this condition. Well, then we have, what do we have? So we have an interval, and we have two continuous functions. They're actually better than continuous. They're differentiable, and even the derivative is continuous, but never mind that. We have that y1 of 0 is equal to a, and that's equal to y2 of 0. So they coincide at one point. And now the Picard-Lindelöf theorem said that because there were two solutions, if you restrict the interval, right, to looking at this little interval around 0, well, then there was a unique fixed point, right? So this means that in a small neighborhood of the origin, so 2, in a small neighborhood of the origin, and this is thanks to that in the contracting mapping theorem, you had a unique fixed point in a small neighborhood of the origin, y1 is equal to y2. Right? But actually, the Picard-Lindelöf, the argument would work at any other point. Right? Suppose you take any other point, then you take a solution to the ODE. Well, if you take another point, then the value. So if you take any other point. So here you have 0. And so now take any other points, let's call it x0. And if you assume that these two functions coincide at this point, so suppose that y1 of x0 is equal to y2 of x0. If you now restrict this interval, make it sufficiently small, then the argument of Picard-Lindelöf tells you that you had this unique fixed point. So you had a unique solution on this little interval. But since they coincide at this point, it means that they must be the same in this little interval. And so you see that now we have the condition for the lemma. Okay? For the lemma that said that, so you have these two continuous functions, and they were equal at one point. And if they're equal at a point, then they're equal in the whole neighborhood. Okay? So these two functions, these two solutions are equal on the interval where they're both defined. Okay. Now, okay, so now you might, and then I want to do a little bit of review at the end, so at least say something about the final. But before we get to that, let me just make one more observation about the Picard-Lindelöf. So you may say that in the proof of the Picard-Lindelöf, we kind of had to restrict the interval. Is that really necessary? Why should we restrict? Why should we only be able to say that we had a solution in a very small interval? And so if you're looking at the example, suppose you're looking at the example where f of y is equal to y squared, g of x is equal to 0. And so you're looking at the ODE, the solutions here, y, so that y prime is equal to y squared, and let's say equal to a for x equal to x0. Okay, so suppose you're looking at an ODE like this, right? So at this x0, you want the value of the function to be So you want, y of x0 equal to, maybe I should, maybe this is a little bit bad notation. So I want a function so that y prime is equal to y squared, and I want y of x0 equal to a. Right? Okay. Now let's say that x0 and a are both positive. So if you're looking at this ODE, then you can just, this one here is easy to solve because you have a function y prime equal to y squared. And now let's try to find a solution in a neighborhood of x0. But there it's supposed to be positive. So in a small neighborhood it's positive. So I can divide by y squared. So I can looking at, so this thing here is equivalent to that y prime over y squared is equal to 1. And this thing here I can write as 1 over y prime times minus 1. This thing here, if you're looking at this function here, by the chain rule, it's equal to that, right? And so this means that now you can apply the fundamental theorem of calculus. And if you're integrating this function here, and you're integrating it from two values, x0 to x, d of s, sorry, this is the prime. Then what you get is that this thing here is equal to, well, on one hand, by the fundamental theorem of calculus, it's 1 over y of x minus, and then there's a minus sign, sorry, this here, because of this minus sign. So it's minus this plus 1 over y of x0. And on the other hand, it's equal to this. And when you're integrating this on this interval here, so it's also equal to x0, x, and then 1 ds. This thing here is just x minus x0. X minus x0. Okay? So if you solve it, then let me just write the result. If you check what this gives you, this gives you that when you solve it like this, you're getting that y here is, so you have this ODE here, and you're assuming that these things here are positive, and then the solutions are of the form y of x equal to a over 1 plus a x0 minus x. Fine. And so what you should observe here is that this thing here, right, as this is not defined, so this is note that y is not defined on all of R, but instead as x here goes to x0 plus 1 over a, as x0 goes to this thing here goes to minus 1, so the denominator goes to 0, so the function blows up. Right? So this here shows you that it does, in a neighborhood of this point, it has a solution, but that neighborhood is not, it's some relatively small neighborhood, and the function, you cannot extend it past, past a certain value. You can't extend it past, in this case, you can't extend it past this point here, so to the left of this point. To the right, I guess, of that point. Okay. Okay, so now I want to say a little bit about the final. Yeah, sorry.
Why is it that you can't, once you reach that point where it blows up, does it like, it never solves the differential equation past that point?
Yeah, that's right. So the thing is, right, so this here, this ODE is going to force it to, once y become large, then y become really, really large. So it becomes large too quickly, so it becomes quickly so it would give you some sort of ODE like this, that you have some critical value where you couldn't extend it past that because it will have like a tangent that is going vertical like this. Okay, and so you can't. So this means that there's, that's right. So you have a solution that exists on some interval, but it doesn't exist past this point. So you can't have a solution, on some interval larger than this to the left. And there's probably a similar phenomenon on the other side, right? Okay. And it's like a kind of standard issue that for differential equations you can get blow-ups like this. That is a particular simple example. Any other questions? Okay, great.